Peter, do you know how to use eigenvectors to solve this linear system of ODEs?
Oh, I know this. Just put it in a calculator. Boom, solved.
No, you imbecile. Let me show you. Let's first put our system of equations in matrix vector form. X prime is the vector of the first derivatives, A is the coefficients matrix, and X is the vector of the original functions.
Okay, I'm following. So we need to find the set of all solutions X in CRR3 that satisfy this system.
Right, so let's call that set of solutions as S. Our problem now boils down to finding a closed form for S. Now obviously we know S is a subset of CRR3.
Yeah, that makes sense. The solution set is a subset of all possible inputs.
But the important idea here is that S is not just a subset, it's also a subspace.
Wait, why does that matter?
Because if S is a subspace, then it has a basis. If we can find that basis, then we can express every element in S as a linear combination of that basis. So now, the problem has reduced to just finding enough solutions to form a basis for S.
Oh, that makes sense. But how many solutions is enough to form a basis? We need to know the dimension of S for that, right?
Yes. In general, S has dimension n if it's a subset of CRRn. This is provable by constructing a linear isomorphism between S and Rn.
Okay, I see. So for n functions in the system, we need to find n independent elements in S to form a basis.
Correct. Let's find the n basis functions then. Say our basis is composed of n functions, f1 through fn. Recall that by definition of being a basis, these functions must satisfy two conditions. First, each function f must be an S, so it must satisfy f prime equals a times f. Second, all functions must be linearly independent.
It still seems like a pretty hard problem, though. How do you do that?
Let's look closer at the first condition. You might notice that f prime equals a times f looks almost identical to the classic setup of y prime equals k times y for some scalar k, where we'd make y some exponential function.
All right, I remember that. But A is a matrix, not a scalar, so that's useless?
No. We just have to make A act like a scalar, and A acts like a scalar when applied to an eigenvector. So if we make f output eigenvectors, then A times f turns into lambda times f. So f prime equals lambda times f.
Oh, that's clever. So we can just make f be an exponential function with an eigenvector factor.
Precisely. So for an eigenvector v and its eigenvalue lambda, we define its corresponding basis function to be f equals e to the lambda t times v.
Wait, but that only solves the first condition. What about the second one? The functions are in S, but are they linearly independent?
If A has n independent eigenvectors, then yes, they are. The functions point in eigenvector direction, so they're linearly independent. You can evaluate at t equals 0, for example, to prove it.
Oh, wow. So we knocked out both conditions just by using eigenvectors as a solution to satisfy the first condition.
In the end, each basis function is an eigenvector exponential, and each solution x in S can be represented as a linear combination of this basis.
So to find all solutions to the system of ODEs, you just find a basis for the solution set consisting of exponential eigenvectors?
Yes, follow for more.